All right. Okay. Hi, everyone. Thank you for joining the Astro seminar. Sorry for the long break for the past month because we had so many conferences going on. Today we have Dr. Lucy McNeill talking to us today. As you all know, she is at Monash and she just obtained her PhD in May, and now she is heading off to Japan in about a month to work as a JSPS fellow at the Kyoto University. And today she will tell us about her recent work on rotation in massive stars and their remnants. So yeah, please take it away.
Thanks, Joe, and thanks for the invitation to talk today, and thanks for everyone for joining as well. So yeah, I'm Lucy. I did my PhD in the School of Physics and Astronomy, and today I'm going to show you some work about what we can learn about rotation in massive stars and their remnants from 3D simulations of oxygen shell burning. And this work was done with and supervised by Bernard Mueller. Oops, sorry. Okay, so today I'll give a quick overview of the angular momentum transport problem in the context of massive stars. So I'll go through the first project, which is about differential rotation in rapidly rotating stars. So I'll explain a big motivation for this project, which is basically a clash between observations of the solar convective zone and theory. And then I'll kind of systematically go through some results that tell a pretty coherent story about what's going on there. And then we'll move into sort of the non-rotating regime and think about what might be setting the birth spin rates of neutron stars. So in particular, we'll look at one mechanism, which is stochastic spin up from internal gravity waves or buoyancy waves in these progenitors that are generated by the very vigorous convection that occurs in them. So I'll explain the mechanism and how you can model it as a random walk. And then we'll go through some results in detail, and then finally kind of talk about what this might mean for the neutron star spin population. So the birth spin periods of neutron stars are generally tens to hundreds of milliseconds, maybe closer to 100 milliseconds, but there's obviously going to be a variety in the birth spins. So for example, the Crab pulsar is inferred to have been born spinning at around 40 hertz. And then on the other end of the spectrum, there's slower pulsars, such as this one, that are born spinning around 2 hertz. But yeah, the number to keep in mind is maybe close to 100 milliseconds or so. So if we try and think about where this comes from in terms of the neutron star progenitors, so you have you know, a massive star undergoing the final phases of burning. Eventually, you know, the iron core is going to collapse and the star will explode. And the key thing that's maybe setting the birth spin is angular momentum conservation. So, you know, the thing that you know, becomes the neutron star, what was the angular momentum of that material before it collapsed? And that should be conserved. And then if you account for, you know, the new radius of the neutron star, that can maybe set your birth spin period. So if we do some, or if you did or ran some stellar evolution models to explore this kind of question, you would get neutron stars that are born spinning in the kilohertz range. But given what the inferred birth spin population is, there must be something that's sort of slowing these down before that point by a factor of about 100. So one example is spin down from magnetic torques. So that's where you have a magnetic progenitor that's differentially rotating, and you have the field lines twisting around, and they, this twisting keeps happening, and then these field lines break and reconnect. And I think that process is thought to redistribute angular momentum out of the core. And for example, this Hager 2005 study finds that you can slow things down by about a factor of 10 or so to have these burst spin periods that are 10 milliseconds. So it's an improvement, but it's still really, really fast, even compared to the Crab pulsar. So we're gonna kind of keep thinking about this particular mechanism, and because it requires differential rotation, to move on to talking about that specifically. So I think differential rotation is important for understanding massive stars and remnants, maybe for these two reasons. So as I mentioned, that spin down process that is able to slow the spins down relies on differential rotation in the polar angle theta. And another reason is that the formation of millisecond magnetars requires really severe differential rotation, in that the core, so smaller radii, have to be very rapidly rotating. But in both of these theories, there are lots of uncertainties, and they're hard to model. So instead of approaching things using those kinds of questions as a starting point, I think we need to go back to some really basic questions about differential rotation. So the sun is a reminder of how little we understand about differential rotation in convective zones. So this is the rotation profile of the solar convective zone. So you can see that at the equator, the frequency is about 20 to 30% faster than closer to the poles. So if you thought about, instead of going to the observation, if you thought about how should convective zones rotate from a theoretical point of view, so you're considering, so you have this shell, so it's convective, so it's unstable to convection. It should be stable to rotation. You have to consider maybe things like shear and these magnetic instabilities, but whichever one you look at, or whichever combination you kind of use in the framework of a stability analysis, you're still left with convective zones should rotate either rigidly, so constant omega, or with constant specific angular momentum. So that would be where the frequency is slower at larger radii. But yeah, as we saw with the sun's not doing either of those. So we're going to kind of address that question. But yeah, as well as the sun, there's also dozens more main sequence solar-like stars that also have those patterns observed, of sometimes up to 50% faster at the equator. But the reason that we're looking at massive stars, or why massive stars are so advantageous to address these questions, not only because we're interested in the remnants, but it's a timescales question. So 3D simulations are very, very expensive to run. We can only run them for on the order of maybe 10 minutes, and And during late burning, unlike, the sun right now or something, so the nuclear, rotational, and convective timescales are all on the same order. So if there's anything, uniquely 3D that's presenting itself in these simulations, we should be able to resolve it, even in these very short simulation times. Okay, so to look at differential rotation, we use a 16 solar mass helium star whose oxygen shell is initially rigidly rotating at 72 millihertz. So that's really, really fast, and would leave behind one of these really fast neutron stars or a black hole with this spin parameter if there's no like angular momentum transport or anything happening in late burning. So this is the shell structure of the model. So it goes from about 4,000 to 36,000 kilometers, covering 3 convective burning regions. But we're only going to focus on this inner oxygen burning region because it has the shortest convective turnover time. So it's kind of our best bet for noticing any of these sort of uniquely 3D hydrodynamic effects coming up in the convective region. So first, let's look at some profiles of the specific angular momentum and the angular frequency. So we'll start with the lower panel. So here in black is the initial condition of rigid rotation. So the corresponding extents of the convective regions are shown with their times in the dashed lines here. So at time is 0, you have just a flat omega. And then as time goes on average, well, you get a positive frequency gradient that might even get a bit steeper in time. So at least from this, we can say that even though it started at a rigidly rotating configuration, it doesn't seem to want to stay there. It even looks like it's moving away from that. So we can also look at the specific angular momentum L, which was another one of these predicted configurations with stability analysis that things will tend toward constant L. So again, if we look as time goes on, maybe on average as time goes on average, maybe this profile is getting steeper. It's kind of hard to say, but from this figure, but at least we can say that it doesn't seem to be trying to go toward constant L. So yeah, maybe we can quantify this a bit more robustly. So if it's true that the convective region is tending toward constant specific angular momentum L, then we should be able to formulate it as a diffusion process. So the reason is that when we look at the averaged angular momentum transport equations, there's only one term, this turbulent flux term, that like covers things that are happening because of the turbulent convection. So any angular momentum transport from these convective processes will be captured by this term. And if LZ is tending toward a constant, then we should be able to say that that flux goes like the local spatial gradient of L. So we plotted this. So maybe if we look at the hot pink curve first, that's our gradient approximation, which includes a bunch of like mixing length parameters and other things to do with convection, but that's this is the kind of turbulent flux we would expect if our convective zone tends to want to go toward constant L, but we plot the actual flux in the lighter pink color. And so we note that it's got the opposite sign to what you'd predict in this kind of framework. So kind of like we suspected from that, the plot of LZ that I showed before, it doesn't seem to be tending toward constant L either. So we can maybe confirm this with some 2D rotation profiles as well. So this was the initial condition for the oxygen shell. So remember, it was rotating rigidly at 72 millihertz, and we're just plotting the cubed root of the angular frequency here, just to kind of see the finer structures. So yeah, that's the initial condition. And then at, say, 400 seconds, this differential rotation pattern is there, where, you know, similar to the sun, it's about 30% faster at the equator compared to higher latitude values, which we kind of suspected already from the those black and gray plots before. Okay, so at the moment, it seems that the convective zone doesn't want to adjust to rigid rotation or constant L. In fact, it seems to be rotating pretty stably to be faster at the equator. So maybe to explain this, we can go back to thinking about the sun. So about 10 years ago, there was this series of papers that you know, proposed to explain why the sun rotates 30% faster at the equator using thermal wind balance. So thermal wind balance is, well, it comes down to just a force balance for our star. So you have pressure gradient, and you have gravity, and then you have inertial forces from rotation. And the idea is that, you know, everywhere in your convective region, this should be balanced, no matter what the pressure gradient is and all of this. So it's maybe a more familiar concept in earth sciences or meteorology. So on the Earth, we have hotter air at the equator and cold air at the poles. So there's a temperature gradient from the equator to the poles that actually drives these convective motions in the upper atmosphere. So I think this figure summarizes their results best. So if the solar convective zone is dictated by the thermal wind equation, then the rotation frequency, the contours of that should match the contours of an entropy function, and in particular, it's the entropy fluctuation. So the total entropy minus the mean of the whole shell is the fluctuation. So it's the contours of rotation should match the deficit of this thing. So we tried to do a similar plot, and this is what we got. But again, just note that we're plotting the cubed root of things to see, you know, the gradients a little better. So yeah, that was our rotation profile, and this is our entropy fluctuation deficit. And you can see that particularly at the equator, there's a good match. So I think we'll just leave this as speculative for now, because we couldn't actually, you know, quantify a force balance in this simulation, but maybe this is an indication that, you know, it's playing a role. But another indicator of the thermal wind balance being in action is that we find, so here we're plotting the polar velocity, so velocities in theta, and I'm just plotting the radial velocity on the right here on the exact same scale, because this is sort of traditionally the probe for convective motions. So we see that, you know, there's similar velocities to this VR, and we're seeing these large scale equator to pole circulation over very, well, over the simulation timescale, or like the convective timescale. So if we think back to doing that diffusion approximation, so seeing if things are tending toward constant LZ using mixing length theory, and we saw that the you know, these things had opposite signs, so it wasn't. If we tried to do the same thing for the, so are things tending towards rigid rotation, you get, so this came from the averaged angular momentum equation. If you do the average angular momentum equation, but now expanding around omega, not L, to get or to look for a diffusion approximation, you end up getting, yeah, a term that you can cast similarly like this, so your gradient approximation. But unlike in this case, you get this extra term in your decomposition, which this actually follows that circulation here. And this isn't new, this has been known for nearly 100 years now, that there's this extra source term when you try and cast your angular momentum transport from convection to a diffusion equation, you get this extra term. So maybe all of these things together might indicate that this thermal wind balance is acting, and we can't rely on you know, considering marginal stability to tell us how convective zones should rotate. So maybe instead it's more like a competition between, so, you know, because we saw that the rotation profile is closer to rigid rotation than constant L, maybe it's like competition between diffusion toward constant omega, and then you have also this unavoidable transport by that circulation that's driven by rotation anyway. Both of these things competing, and then maybe that's the resulting rotation profile. So just to summarize all of that, so yeah, even massive stars, their convective zones, like the sun, rotate about 30% faster at the equator. So this might mean that you know, objects like millisecond magnetars are more difficult to make if it's the case that you know, angular momentum prefers to be further away from the rotation axis. But maybe it's good news for magnetic torques, because that whole mechanism relies on differential rotation. And then I think if we actually want to you know, robustly quantify whether thermal wind balance is acting, I think we need to start with a configuration, so 3D again, but maybe use such a rotation profile as the initial condition, and then maybe it's not so noisy that we can quantify it. And then, yeah, if you want to think about remnants and populations and things like that, we'll need to figure out a way to formulate this for 1D stellar evolution codes, which I think will be really interesting. So yeah, at the moment, we've looked at sort of the first question, which was how do convective zones rotate, and what does this mean for things like spin down from magnetic torques, which is, you know, one proposed way to explain the much slower observed spin population of neutron stars. But now we're going to move on to, you know, what is setting the burst spin rates of neutron stars. So we're going to look at one process in particular, and it's stochastic spin up of the progenitor core from internal gravity waves or buoyancy waves that are generated from turbulent convection. So I just want to emphasize that, you know, unlike the rapidly rotating model before, here we're looking at like a model with no spin. So what that means is we've assumed that something like some very efficient process like magnetic torques or something else we haven't even thought about yet has spun down the progenitor to be really, really slow. So we're looking at, if you're starting with very, very slow spin, you know, what is the, I guess the maximum spin period of neutron stars when they're born? So like the slow end. So I'll explain how this process works. So we have this massive star undergoing late burning, but you know, it's not spinning, or it has very, very slow spin, negligible spin. But you know, in any case, you still have really violent burning in, say, these two blue burning shells here. So you have convective overturn and maybe overshooting, hitting the boundaries. And then what happens is, in these convectively stable regions in red in between, you can get these gravity waves propagating through there. So if you focus on, you know, a convectively stable core and think about, yeah, the convection hitting the boundary, generating waves inside here, they're eventually going to just deposit, like when they break, they'll just deposit their angular momentum in the core. So the idea is that that leads to like a net spin up from all these randomly oriented angular momentum vectors associated with these you know, waves being generated, and you know, therefore the core's angular momentum should increase like a random walk to be spun up. So we're definitely not the first people to look at this problem. So this study by Jim Fuller and others looked at this problem using the 1D stellar evolution code MESA. And yeah, maybe the main takeaway for us at the moment is that their conclusion was, from this stochastic spin-up process, neutron stars cannot be born spinning slower than 500 milliseconds. But if we think back to, you know, what are typical birth spin rates of neutron stars, which was around, you know, closer to 100 milliseconds, you know, you can probably guess that their conclusion is that, you know, this isn't much of a constraint, and it's probably not a dominant mechanism that's setting the spins of neutron stars, you know, if they're able to be spun down efficiently before these late burning phases. And then, yeah, as well as that, after that 2015 study, there's another study from Bernard Mueller and others, which was before our study, which found that, you know, they can make a 3D model that has zero spin in the progenitor and then explode it. And because the explosion itself is asymmetric and you need to conserve angular momentum, they end up with neutron stars spinning in sort of the tens of milliseconds band. So yeah, sort of between now and 2015, there's already something that's more efficient than that 500 millisecond bound. So we model a 3 solar mass helium star, and it's run for 8 minutes during oxygen burning again. So here is the shell structure. So we just have, for most of the simulation, just this oxygen burning shell and carbon. And then there's this convectively stable region in between them here, and then another outer convectively stable region here. And to put sort of how violent the burning is into perspective, that oxygen region, which is only extending 3,000 or 2,000 kilometers or so, has the luminosity of 10 to the 14 suns. So yeah, really, really vigorous. And I'll just show some 2D cross sections of the star. So we're plotting the radial velocity maybe as a tracer for wave fronts. So in this outer convectively stable region, we can see that there's a octopolar mode, and then at a later time in that same outer region, well, at least here, we can see some quadrupole mode. So yeah, before we talk about the mechanism, we'll just recap the basics of a random walk. So you start at some origin, you take a step in a random direction, and then once enough time has passed that you forget which direction you came from so that it doesn't inform your next step, you take another step. And then after long enough time, you'll see that your distance from your initial position goes like the square root of time, or equivalently, the square root of the number of steps you took. So you can apply this kind of process to the angular momentum in the core of that stochastic spin-up process, because it's initially 0, but you can say that the change in angular momentum goes like the number of steps taken times the typical angular momentum sort of in a wave step. And because we have this simulation data, and it's really, really simple for us to measure angular momentum fluxes, we want to recast this in terms of that. So what you have to do there is, okay, so you write the flux, and then you have to make an assumption about your time between steps, which is taken as the convective turnover time in their model. So first, let's just ask, does this random walk at all? So in red is the change in angular momentum, delta J, from the oxygen burning region. And then in black is that random walk model, which uses the angular momentum flux and the number of steps, which includes the convective turnover time and the convective turnover time here. So I guess the the point is that it does seem to random walk. So our measured angular momentum compared to what a random walk model would say. But it's about a factor of 8 difference between red and black. So the thing to note was that assumption of the convective turnover time, which ends up being a factor of root tau. So that just means that the correlation time, so between your steps, is about 64 times shorter than the convective turnover time, which is assumed in that the MESA study. So just to summarize it so far, it does random walk, which I think is pretty cool because, you know, random walks are something that are maybe just left to the realm of like classes and things like that. But, you know, we see this thing play out in something as complicated as, you know, a star that's about to explode. So I think that's pretty remarkable. But yeah, we do note that there was a difference sort of for using a random walk model, where our random walk is best described by one that has a correlation time that's shorter by 50, 100 compared to the convective turnover time. So maybe this means that the steps are kind of losing their memory 60 times faster than you'd otherwise think in this model. So I think we've already seen most of this slide. So this is just, you know, the change in angular momentum in terms of your flux. So yeah, if we want to start talking about neutron star spin, we have to make some further assumptions here. So, okay, the first thing that you can do is, so this is a well-known relation. So you can write the angular momentum flux in terms of the energy flux with this factor of the convective turnover frequency and the wave number that you're interested in. So what they do, so this is like angular momentum in waves of a particular m. But what they say to simplify things in this MESA study is that, okay, let's just set m equal to 1 to kind of simplify things so that we can just ignore m from now on. So if that's the case, you can just write that the flux looks like this. And then the next step, which is also a frequently used relation, is that you can write the energy from waves in terms of the convective Mach number and the burning luminosity of the shell. So just to reiterate that, the next steps were to assume that all angular momentum transport is dominated by a particular wave number, and that's m is 1. And then the next step is that you write the energy flux from waves in terms of the Mach number and luminosity. So if we, you know, carry through these assumptions and use our convective luminosity and Mach number, we get this cyan curve. So this is the, if we just assume that all of this was true, so all the assumptions in the 1D study were true, this is the curve for the spin up that we would get. So this is a factor of 1,000 larger than what we actually saw. So let's try and explain that. The reason is, okay, so if we look at this plot here, this is just the ratio of the angular momentum flux to all of this. And just remembering that one of the key steps was assuming that all the transport is described by m is 1. So yeah, we plot that ratio and find that it's even smaller than 100th. And then if we think back to this relation, then that implies that m is a fraction, which is not possible. But we think what's really going on is that, the reason that the angular momentum flux is so much smaller than, the way you write this energy flux is because, maybe it's not appropriate to make that assumption that all the transport is dominated by a single wave number. So yeah, we think what's actually happening is that because it's not really spinning and it doesn't really have a preferential direction, that waves of around equal amounts in both the positive and negative m, or prograde and retrograde, are generated. And then maybe it's sort of the difference between the two, which is actually random walking. So you instead get like a cancellation, but the difference still random walks. So yeah, just to repeat some things, the difference between, the measured angular momentum was in red. The angular momentum assuming a random walk model, where the convective turnover time is the time between steps, is in black here. So the difference between these two implied a correlation time that differs by about 100. And then the difference between the cyan curve and the other two is explained by that relation for the energy flux in waves. So the assumption that everything's explained by one particular wave number. So yeah, if we remember that other study, they their conclusion was neutron stars have to be born spinning faster than 500 milliseconds. So just say we kind of naively put this here. So say, okay, the cyan curve with all their assumptions must be associated with a 500 millisecond birth spin. Does that mean that our actual curve for what the angular momentum does implies a birth spin rate of 500 seconds? Well, if we think about sort of the trajectories of these curves, so core collapse will happen in hundreds of seconds, and just keep in mind that the breakup angular momentum of a neutron star should be at like 10 to the 50 here to get those sub millisecond spins. So yeah, if we actually turn these curves into a birth spin rate, this cyan one would actually give a sub millisecond birth spin rate, and our red curve is more like 100 milliseconds. So sorry if that's confusing, but I'll try and explain why these spins are different. So yeah, the main difference is that in this MESA model, they used a burning luminosity that's maybe more appropriate in an earlier oxygen burning phase. So they use 10 to the 10 solar luminosities, whereas we measure 10 to the 14, which is more appropriate for sort of the really, really late, just before collapse burning. So I'll try and put all that together so that it makes sense. So, okay, the red and the black, so the actual and random walk model differed by a factor of 10. So where the random walk model overestimated. And then the angular momentum flux that comes from waves was overestimated by a factor of 100. And that was because it's likely that, you know, prograde and retrograde waves are the angular momenta cancel. And then the final thing to explain the difference is that the convective luminosities that were sort of used to answer this question about neutron star spin was underestimated by a factor of 10,000 in the MESA study. So this means that our simulation predicts spins about 10 times faster than 500 milliseconds. So to summarize all of that, so we saw that the angular momentum does follow a random walk, which is pretty cool. But this random walk process is less efficient because of that correlation time issue. The second thing to note is that we found that it's not appropriate to use that single mode wave packet model from the 2015 study. And yeah, the third thing to note was that you know, these neutron star burst spin rates, they do rely very sensitively on you know, what you're saying is the burning luminosity that's sourcing the waves, which was underestimated in this MESA study. So yeah, in the end, we get that stochastic spin up from these gravity waves will give spins that are 10 times faster than 500 milliseconds. But like I've mentioned before, since then, there's other mechanisms that set even tighter constraints on the slowest neutron star birth spin rates. So yeah, we don't think that it's a dominant mechanism either, despite you know, these different results. So yeah, the main takeaways from today is that I'm surprised that even convective zones in these massive stars, just before they explode, seem to be doing a similar thing to the solar convective zone. Maybe the thermal wind equation explains it, but we can't really quantify that in this simulation. And then, yeah, the other conclusions is that the stochastic spin up and its random walk process are less efficient than was previously thought, but including more realistic burning luminosities at the right times actually lead to faster burst spin rates. And yeah, we think it's unlikely to explain the spin population. So thanks for listening, and yeah, happy to answer questions and chat afterwards.
Thank you very much. It was a very, very interesting talk. Does anyone have any questions? You can raise your hand in the Zoom feature or type in the chat box. So while we're waiting, if I may ask the question, so all these 1D simulations, as far as I know, assume this sort of cellular rotation, right? But your first simulation kind of showed that it's not really a cellular rotation. You have like faster things in the equator and stuff. How much does this cellular assumption like affect like the analysis? Like how wrong is that?
So I don't think it's like too wrong, like in terms of the numbers and stuff. So I think, yeah, if they're only rotating like tens of percent faster at the equator, like I don't think that's, you know, maybe what we're seeing just in these late phases isn't you know, so much of a big deal, but maybe it's more that, you know, because there's a 2D simulation and a recent 3D simulation that see an adjustment to constant specific angular momentum. So I think maybe that's a bit more dramatic for that compared to the cellular rotation assumption. Like I think, yeah, I think that kind of hinders anything that relies on constant L more, I think.
But so in your simulations, how do you treat the inner boundary condition? So is that a cellular rotation at the inner boundary?
Yeah, so it's mapped from Kepler,
yeah.
So the 1D code. So it has the same initial condition, and then I think for the contraction of the core, that also is given by Kepler as well.
Hmm. Yeah, I was wondering, like, if you can somehow relax this cellular rotation at the inner boundary, would it affect the cellularness of the rotation? But yeah, I guess it's hard to tell.
Yeah.
Okay, we have another question from Reinhold. Do you want to read it out, or shall I?
Sure, yeah. So yeah, I'll just read it directly out of the chat. Somewhat a real question, but compared to a 1D model with what we now know as the incorrect spherically symmetric rotation, how much do you expect a model with non-spherical symmetric rotation that's more correct to affect the remnant mass? I mean, I imagine the shape might be distorted. Would that have any effect on the mass, or would that not do much?
I'm not too sure because we don't run any of these to the like to when it explodes. But sorry, I don't understand with the mass. How come the mass might change if we implement a different profile or something?
I'm just trying to think of if the rotation should have any effect at all on the mass, or if the two are decoupled. I didn't know if there's something that you thought about, but
yeah, I haven't really thought about that, to be honest.
Okay.
Maybe someone else has thought about it. I don't know. Sorry.
Sure. Thank you.
Lucy, maybe following up on Reinhold's question, I guess, you know, one way to parse that question is to ask if rotation is going to change the compactness parameter, for example, which we know has something to do with the explodability of the star. I guess the question there is, for the typical rotation rates you're considering, is the rotational support actually significant? So, like, for example, what's the kinetic energy in rotation versus the binding, the gravitational binding energy?
So I think to answer the first question, so yeah, I think thinking about, like, to say in this profile, thinking about a like, so if when it explodes, you know, it out to some like radius or mass, it's going to keep all that material and blow away the rest of it. I think it's like, yeah, when you're this rapidly rotating, I think it's kind of weird to think about a mass coordinate there, like if it is deformed and stuff. So yeah, I don't know, maybe it would affect sort of the mass coordinate that you, or like, yeah, effective mass coordinate you're going out to and keeping all that material because of the differential rotation. But yeah, I don't know.
Thank you.
Yeah, it's a good question. And I think, yeah, with I can maybe show, like if you're interested in the kinetic energy, I think of the kinetic energy compared to the convective energy, which is just given by the Rossby number. Sorry. Yeah. So yeah, I think that's the Rossby number. So I think it's like it's pretty severe. So yeah, I think smaller Rossby number is like more severe kinetic energy compared to the convective in rotation.
Okay. Are there any other questions? Yeah, I also had another question, if, if I can.
Yeah.
So you use this like 10 solar mass unit star, was it? I think, yeah, I think you used it. I know you used a 16 solar mass unit star, right?
Yep.
So that's a quite big core. Would you expect a similar behavior for like the more normal massive stars, like 3 solar mass unit cores? I mean,
Yeah.
these are probably the ones that form black holes, isn't it?
Yeah, I think so. Yeah. So yeah, the thing with the, so I suppose the so with this really massive one, like all of the rotation and the convective turnover times are around the same. But then if you, I think in this like that 3 solar mass non-rotating model, I think the convective turnover time is just much shorter. So maybe, yeah, I still think you would like, if a differential rotation pattern presents itself, you should be able to like see it as well. But I think you're in kind of, so maybe if we look back to the thinking about the thermal wind stuff, it's like the, you know, this entropy gradient is like so big and it's driving these winds, and we can see that maybe if it's not really yeah, I mean, as long as you put an appropriate like sort of rapid rotation in, I think you'd expect to see it. But then maybe you know, as you move to slower spins, maybe you wouldn't get this kind of stuff happening, because there's no like pressure or sorry, temperature or entropy gradients to be driving that kind of stuff. But yeah, it could be cool to just see what's the, you know, do a similar thing for the you know, put it at the same fraction of the breakup rotation rate for, say, maybe a 3 mass. I don't know, but maybe there's reasons why you can't do that that I'm not thinking of.
So do you think the ratio between the orbital, well, the spin period and the convective turnover time scale is kind of
I think at a first glance, yeah, just like, because I think you're safe if, because we're running it for minutes, if you can make them all tens of seconds, then like, you know, you can rely on something that's kind of stable happening, I think.
Okay, thank you. So
Cool.
yeah, we've slightly exceeded the hour, so let's stop here. But yeah, thank you again, Lucy, for the very nice talk.
No problem. Thanks for having me. And I'll think about those questions I couldn't answer.
And yeah, good luck on your next month and your future in Japan.
Cool. Thanks.
Okay, bye everyone.
See ya.